Well, welcome back to our class on discrete mathematics, looking at discrete structures, and we're continuing to make some good progress as we go through Rosen. And in this chapter, we're going to be focusing on counting, trying to give a nice overview of the things that we've covered up to this point, breaking it down into pieces. And Rosen is fairly eloquent in giving a lot of depth, so much depth that it can feel a little bit overwhelming at times. And so once again, I'm going to try and keep this at a higher level and won't get into the details of some of the proofs, but try and give you a basis, a framework that you can get a sense to how these things are useful. And so I will be continuing to be focusing on applications. So for this chapter, this is what we're going to focus on. We'll get into the basics of counting, something called the pigeonhole principle, permutations and combinations. And so this is going to be coming up in several sections. And so get familiar with some of this nomenclature and how we show it. We'll talk about binomial coefficients and identities. And then we'll have a discussion on generalized permutations and combination, what that means. So that's the focus. The last part isn't included, but it is in Rosen if you want to read about that. So combinatorics is the study of arrangements of objects. It is an important part of discrete mathematics. Its subject was studied a long time ago as the 17th century when combination questions arose in the study of gambling games. Maybe a little bit of a perspective of the history, but it has many other applications. Enumeration, the counting of objects with certain properties, is an important part of combinatorics. We must count objects to solve many different types of problems. For instance, counting is used to determine the complexity of algorithms. So we can see a computer science related application. It's also is required to determine whether there are enough telephone numbers or internet protocol addresses to meet demand. We'll have a chart that shows some things there that you can get a chance to see how that would apply. So some practical applications. And recently it has been played a key role in mathematical biology, especially in sequencing DNA. So even in biology, we can see some interesting thing, and I'll have a chart on that as well. Furthermore, counting techniques are used extensively when probabilities events are computed. So let's give some perspective of what we cover, the basic rules of counting, which we'll study in section 6.1. So this will be the beginning of the lecture, can solve a tremendous variety of problems. For instance, we can use these to enumerate the different telephone numbers and that could be possible in the United States, given some different criteria for how we use those digits. The allowable passwords on a computer system and the different order in which the runners in a race can finish. Another important combinatorial tool is a pigeonhole principle, and that's going to be covered in the second section, 6.2. This states that an objects are placed in boxes, and there are more objects in boxes than there is a box containing at least two objects. For instance, we can use this principle to show that among a set of 15 or more students, at least 3 were born on the same day of the week. We can phrase many counting problems in terms of ordered or unordered arrangements of the objects of a set with or without repetitions. These arrangements, called permutations and combinations, are used in many counting problems. For instance, suppose that 100 top finishers in a competitive exam taken by 2,000 students are invited to a banquet. We can count the possible set of 100 students that will be invited, as well as the way in which the top 10 prizes can be awarded. Another problem in combinatorics involves generating all the arrangements of a specified kind. This is often important in computer simulations, and we can devise algorithms to generate arrangements of various types. So that's a little bit of a perspective of a whole chapter. Now getting into the details, first the basis of counting. So suppose that a password on a computer system consists of 6, 7, or 8 characters. Each of these characters must be a digit or a letter of the alphabet. Each password must contain at least one digit. How many such passwords are there? The technique needs to answer the question, and a wide variety of other counting problems will be introduced as we go through this material. Counting problems arise throughout mathematics and computer science. For example, we must count the successive outcomes of experiments and all the possible outcomes of these experiments to determine the probabilities of discrete events. We need to count the number of operations used by the algorithm to study its time complexity. And we'll introduce the basic technique of counting in this section. These methods serve as a foundation for almost all counting techniques. So specifically, we'll talk about the product rule, the sum rule, the subtraction rule, and the division rule. So we'll go over these quickly. There's lots of examples, and so we'll quickly go over that and also have some perspectives on tree diagrams. So the product rule first, the procedure can be broken down into a sequence of 2 tasks. There are n1 ways to do the first and n2 ways to do the second. Then there are n1 times n2 ways to do the procedure. So this is how we can be thinking about it. So how many bit strings of length 7 are there? Since each of these 7 bits is either 0 or 1, the answer is 2 to the 7. So it's 1 times 2 to the 7, which is 128. How many different license plates can be made? In each plate contains a sequence of 3 uppercase English letters followed by 3 digits. So we have 26 choices for the first 3 and 10 choices for the next. And so it's a product rule, 26 times 26 times 26 times 10 times 10 times 10. And we can see that's 17.5 million different possible license plate in that kind of a scenario. So counting functions, how many functions are there from a set with m elements to a set with n elements? And so we come up with the value here, n to the m such functions. Counting one-to-one functions, how many one-to-one functions are there from a set with m elements to one with n elements? So the product rule tells us there are n times n minus 1 times n minus 2 to n minus m minus 1 such functions. So we can see that is a little bit more complicated than the previous way of looking for that as an example problem. So I mentioned this before, but let's look at a telephone numbering plan, and we'll talk about 2 versions of what this was like. So the North American numbering plan specified that a telephone number consists of 10 digits, consisting of a 3-digit area code, a 3-digit office code, and a 4-digit station code. So that's how it would work. And so we have this kind of designation for each of these digits, X, N, and Y. So N and Y is a 0, 1, N is 2 through N, and X is 0 through 9. And so a little bit of constraints. And so basically, if we look at that, what was the number of telephone numbers in the old plan? A little bit over 1 billion. And then with the new plan, we actually have 6.4 billion for that. And so you can walk through the details and see how that would work. But this is, you can see that this counting is actually has a useful feature for planning. Well, what about counting subsets in a finite set? So we can use a product rule to show that the number of different subsets of a finite set S is 2 to the absolute value of S. And so you can walk through that solution to think about that in more detail. So for the product rule in terms of sets, if A1, A2, up to AM are finite sets, and the number of elements in each Cartesian product of these sets is the product of the number of elements of each set. So The product rule can be laid out as here, and this should be a subscript A1 times A2 all the way up to A sub n is equal to this formulation that we see there. Okay, in terms of DNA and genomes, a gene is a segment of DNA molecule that encodes a particular protein, and the entirety of the genetic information of the organism is called its genome. A DNA molecule consists of two strands of blocks known as nucleotides. Each nucleotide is composed of four bases. I'll just use these letters A, C, G, and T. The DNA of the bacteria has between 10 to the 5th and 10 to the 7th links of these four bases. Mammals have between 10 to the 8th and 10 to the 9 links. So by the product rule, there are at least 10 to the 4 to the 10, all of that to the 5th power, different sequences of bases in the DNA of bacteria, and 10 to the 4, all that to the power of 8, different sequences of bases in the DNA of mammals. The human genome includes approximately 23,000 genes, each with about 1,000 or more links, each one of these bases. And biologists, mathematicians, and computer scientists are all working together to determine the DNA sequence, the genome of different organisms, and they have some interesting ways of coming up with that sequence, which unfortunately is beyond the scope of what I can cover right now. But I do have some thoughts and some papers and some recordings that I have, so you can see that on my YouTube channel. Okay, we talked about the product rule. What about the sum rule? If a task can be done in one of n1 or ways or in one of n2 ways, then none of the set of n1 ways is the same as a set of n2. Then there are n1 plus n2 ways to do the task. And so thus we can see there's ways that we can be just doing, adding the sum of some possible ways. And so this is an example that you can look through. So here is a way of looking at the sum rule in terms of sets. And so this gets into stuff that we've already covered. And this is also something that we'll be talking about more in chapter 8, but I won't go over this in detail for right now. You can also have the combination of the sum and the product rule. Suppose the statement labels in a programming language can either be a single letter or a letter following a digit. Find the number of possible labels. And so you can have a single letter, so this would here, or you can have a letter and a number, and so thus we multiply those together, and we add these, and we get that total 286. Well, here is another example. How would we look at counting passwords? And so combining the sum and product rules allows us to solve more complex problems. So this is an example. Each user on a computer system has a password, which is a 6 to 8 characters long. With each character is an uppercase letter or a digit. Each password must contain at least one digit. How many possible passwords are there? So current passwords, you wanted to have special case characters. This is not what we're including here, but we can start to walk through the kind of numbers that are available here. And so you can see this is a huge number. I'm not going to walk through each one of these elements here, but this just gives you an example for this particular scenario, how many possible passwords that you could have. So even at this level of complexity, that gives you some rarity in terms of just guessing at a password. Here's another example of looking at internet addresses. And so there's different types of classes of addressing. This gets into material for another class. So you have class A, class B, C, D, and E. And so class A addresses are used, the largest networks of 0 followed by a 7-bit net ID, and then 24-bit host ID. Class B uses the medium-sized network, and so a 10 followed by a 14-bit net ID and a 16-bit host ID. class C addresses uses the smallest network, 110, followed by 21-bit net ID and an 8-bit host ID. So thus we can see different ways that we're breaking up things in the Internet Protocol IPv4 version 4. And there are some limitations about that. And thus it was a motivation for updating this to try and have more available IP addresses, Internet Protocol addresses. So how many different IPv4 addresses are available for computers on the internet? And so we can see that. And so this is for 3.7 billion or so addresses. And so we're in a situation where we're running out. And so thus we have IPv6, where we expand the number of digits that are available. So we've dramatically increased the number of internet addresses that are available. Now we have the subtraction rule. If a task can be done either in one of n1 ways or in one of n2 ways, then the total number of ways to do the task is n1 plus n2 minus the number of ways to do the tasks that are in common between them. So we can put that in set notation here, which with our Venn diagrams, you might remember that we covered before. You can interpret this maybe a little bit easier. All the things that A can do, all the things that B can do, but you need to subtract the things that are in common, and that's how we get that. Okay, how about counting bit strings? And so, for an example, how many bit strings of length 8 starts with a 1 or ends with the 2 bits of 0, 0? And so here is a solution. You can walk through that, and we can see that with what we've picked up so far, we can solve this problem, and it's fairly straightforward. The division rule. So there are n divided by d ways to do a task. It can be done using a procedure that can be carried out in n ways. And for every way w, exactly d of the n ways correspond to way w. Restating in terms of sets, if the finite set A is a union of n pairwise disjoint subsets, each with d elements, then n is equal to A divided by d. In terms of functions, if f is a function from A to B, where both are finite sets, and for every value y is an element of B, there is actually exactly d values of x is an element of A, such if f of x is equal to y, then B is equal to A divided by D. So I'm not going to go through the example, but we've gone through all of these different rules, product, division, addition, subtraction. And here is an example of a tree diagram, and you can be thinking about this example might be helpful. So tree diagrams, we can solve many counting problems through the use of tree diagrams, where a branch represents a possible choice and the leaves represent possible outcomes. Suppose that I love discrete math t-shirts come in 5 different sizes: small, medium, large, extra large, and extra, extra large. Each size comes in 4 colors: white, red, green, and black, except extra large, which comes in only red, green, and black, and extra, extra large, which only comes in green and black. What is the minimum number of shirts that a campus bookstore needs to have, one of each size and color available? And so you can be seeing how we've expanded that with the things that we stated about what is available for each size, what are the colors, and then just counting those up, we can get that total number. So tree diagram, graph theory can be a very interesting area, and some of you may want to continue to be exploring that as you move on. Okay, next we briefly mentioned this, but now let's get into some details about the pigeonhole principle. Suppose that a flock of 20 pigeons flies from a set of 19 pigeonholes to roost. Because there are 20 pigeons but only 19 pigeonholes, at least one of these 19 pigeonholes must have at least 2 pigeons in it. To see why this is true, note that each pigeonhole has at most one pigeon in it. At most 19 pigeons, one per hole could be accommodated. This illustrates a general principle called the pigeonhole principle, which states that if there are more pigeons than pigeonholes, there must be at least one pigeonhole with at least two pigeons in it. And we'll see this in the next chart. It's in figure 1 in Rosen. The principle is extremely useful. It applies to much more than pigeons and pigeonholes. So keep that in perspective. So this is just showing what I just talked about here. And so that's putting it into a principle or theorem or whatever, the pigeonhole principle. If k is a positive integer and k plus 1 objects are placed into k boxes, then at least one box can contain two or more objects. You can look through the proof, but that just gives you some perspective on that. In terms of a corollary, a function f from the set with k plus 1 elements to a set with k elements is not one-to-one. I think you can figure that out, but you can go through this proof and see how that works. So I won't go through the details here, but just mention this. So among a group of 367 people, there must be at least two with the same birthday because there are only 366 possible birthdays. So 365 days a year, and then you have leap year. And so those are all the possible things that we could have. So the generalized pigeon principle, if n objects are placed into k boxes, there must be at least one box containing at least n divided by k objects. And we have a proof for that and an example. I'm not going to go through those, but you can see how that flows. Once again, I'll just mention the example, but I won't walk through it. And so A, how many cards must be selected from a standard deck of 52 cards to guarantee that at least 3 cards of the same suit are chosen? And B, how many must be selected to guarantee that at least 3 hearts are selected? So you can be looking at this, and so this gets into some interesting number theory, maybe with card game focus, but that's just an application. You can have any number of applications, and you can walk through this solution. All right, well, let's talk about permutations and combinations. And so there may be some nomenclature and some syntax that may not be familiar to you. I'll try and keep coming back to that and help you through what it means and how we can be using that here. So we're going to talk about permutation, combinations, and then proofs, and we will just lightly talk about the proofs. So a permutation of a set of distinct objects is an ordered arrangement of these objects. An ordered arrangement of R elements of a set is called an R permutation. So P for permutation, and you can be seeing that they use P, and then we have these numbers here to be showing this. And so the number of R permutations of a set with N elements is denoted by N comma R. So here is the formula for the number of permutations. And this is going to be a useful way of presenting that. And so that's the thing that I'm going to focus on here. And you can look through the proof, but this is going to be how we can be coming up with a number, a value. So solving counting problems by counting permutations. And so how many ways are there to select a first prize winner, a second prize winner, a third prize winner from 100 different people who have entered a contest? And so here we have P 100 comma 3. And so we just stick this in this equation and we can solve it. And what you can see, if you were to write this out, there's a lot of things that can cancel out, and it ends up being not as difficult to figure as you might imagine when you first look at this problem. So n minus r is going to cancel a lot of these terms here. And so that's how it makes it a little bit simpler. And we get this kind of not so bad way of looking at things. Okay, solving problems, counting problems by counting permutations. And so I'll just mention the example. Suppose that a saleswoman has to visit 8 different cities. She might begin her trip in a specific city, but she can visit the other 7 cities in any order she wishes. How many possible orders can the salesperson use to visit these cities? And you can see that it can actually be a fairly large number. And so just like when we were looking at other examples, say like password counting, possible password countings, that there's all kinds of different ways that that could come out. Another one, how many permutations of the letters A through H contain the string A, B, C? So once again, we could be using this permutation equation that we showed here with the simplification that I mentioned and come up with a value of 6 factorial, which gives us a total of 720. Okay, now we're going to talk about combinations. We talked about permutations. An R combination of elements of a set is an unordered set of R elements from the set. Thus, an R combination is simply a subset of the set with R elements. The number of combination of set with n distinct elements is noted by C, n, comma, R. And the notation that's listed here is also used and is called a binomial coefficient. And we'll be talking about that shortly, so just keep that in mind. So here we have the general equation for our combinations, and it's similar to the permutation equation. So you can be thinking about that, but there's one factor that's different between them. I'll be showing you both of those on the same slide in just a few minutes. So I will just mention the example, but not go through the proof. How many poker hands of 5 cards can be dealt from a standard deck of 52 cards? Also, how many ways are there to select 47 cards from a deck of 52 cards? And this is kind of interesting if you look at it, that we actually come up with the same number. And so this is a special case of a general result. Which is shown with this corollary that C n comma R is equal to C n minus R. And so that gives you an interesting thing for us to keep in our back pocket. So we'll just mention some thoughts on combinatorial proofs. A combinatorial proof of an identity is a proof that uses one of the following methods, either a double counting proof or a bijective proof, which is a one-to-one relationship approach to be thinking about how we're going to approach solving a problem. So here are 2 combinatorial proofs that we have this, and so you can be walking through how you can be using that to show that these are true. I'm not going to do that in detail for this lecture. We have some examples, and so how many ways are there to select 5 people from a 10-member tennis team to make a trip to match at another school? And so we can be seeing this number here, 10 factorial over 5 factorial times 5 factorial, and we get a number of 252. This is another example. A group of 30 people have been trained as astronauts to go to the first mission to Mars. How many ways are there to select a crew of 6 people to go to the mission? And so we can see it's more than 500,000, as we close to 600,000 for that number. All right, now let's talk about binomial coefficients and some identities. And so some useful things that are of benefit. We'll be focusing on the binomial theorem and also Pascal's identity and triangle. And hopefully the triangle will help you to understand this a little bit better. So as we talked about in section 6.3, the number of R combinations for a set with an R number is often denoted here with this type of notation, or we can be using this, Cn comma r. The number is called a binomial coefficient. So the result of this, because these numbers occur as a coefficients in the expansion of powers of a binomial expression, such as a plus b quantity to the n power. So we will discuss the binomial theorem, which gives a power of a binomial expression as a sum of terms involving binomial coefficients. We will prove this theorem using a combinatorial proof. We also show how combinatorial proofs can be used to establish some of the many different identities that express relationships among binomial coefficients. So I'm just going to focus a few things on this chart, make some observations as we're continuing to try and keep this at a high level way of us getting introduced to these concepts. And so the power of binomial expression. So binomial expression is a sum of two terms such as x plus y. So we can use the counting principle to find the coefficients in the expansion of k of the quantity x plus y to the nth power. And so what we end up finding, so if we have an example of x plus y to the power 3, we're going to have these types of terms, x to the third, x squared y, xy squared, and y cubed. And so what we need to do is to figure out, well, what are the coefficients that is associated with these? And so here we see that there's going to be 3 for some of these coefficients and 1 for others. So keep that in mind. We're going to continue to develop that. And so we get this, this way of having that. So we have this x plus y to the nth is equal to the summation of things listed here. And this is the same as this if we had n is equal to 3. So keep that in mind. And we can specifically come up with this equation. So in that case, this would be n would be 3. And so we can figure out these numbers specifically with what we were showing here. And we had the formula for combinations in the previous section. So that's a little bit of perspective of what I wanted to highlight for the binomial theorem. I'm not going to walk through the proof. You can feel free to look at that. Then with that information, what is the coefficient of x12, y13 in the expansion of this? And so this is one of the elements in this complicated equation here, where when we had to the power 3, we just have a handful of terms. Well, this is a lot more terms, and so we have to figure that out specifically for that. We can do that with this, this generalized equation and come up with a result. And so we show that in the solution, and you can go ahead and pause the video and think about that in more detail. Here is another useful identity with n greater than or equal to 0. We have this value, and so this is the summation is 2 to the n. And so we have some information on that and a proof. I won't walk through that, but that's more things that you can focus on going in more depth with Rosen. Okay, I just have a couple slides on Pascal's identity. And so this is a way of showing that. And the next chart where I introduce Pascal's triangle will be, I think, a way that you can get a better sense of what's going on here. So let me go to the next chart, and I'll just basically come back to this equation in just a minute. And so here is Pascal's equation with this kind of a nomenclature. And then the solution of what those things are, what is that the coefficient, the result for each one of these things. And then we can see this relationship with Pascal's triangle, that these two, the summation of that is what's going to be the coefficient at this level below. So 15 plus 6 is 21. We can see that it lays out. And we can see as we get into higher, the exponent n goes higher, that we have all of these terms and they get larger and larger, the coefficient in the middle. So that's something that gets larger as we go. So this is Pascal's identity. So here we can see, go back to that generalized version, and here is for a specific example that we can see how that would work out. So hopefully that gives you a better sense to be thinking about binomial expansion, thinking about Pascal's triangle and Pascal's identity for us to be working through all of that. Okay, well, let's now think about generalized permutations and commutations. And so this is the material that we're going to be covering for this. And just as a reminder, I put these equations here again to help us to be thinking about this. And so we'll talk about permutations with repetition, combinations with repetition, permutations with indistinguishable objects, and distributing objects into boxes. So if we're thinking about this, in many counting problems, elements may be used repeatedly. For instance, a letter or digit may be used more than once on a license plate. When a dozen donuts are selected, each variety can be chosen repeatedly. This contrasts with the counting problems discussed earlier in this chapter, where we consider only permutation and combinations, which each element could be used at most once. So in this section, we will show how to solve counting problems where elements may be used more than once. Also, some counting problems involve indistinguishable elements. So for instance, to count the number of ways the letters of the word success can be rearranged, the placement of identical letters must be considered. This contrasts with the counting problems discussed earlier, where all elements were considered indistinguishable. So in this section, we will describe how to solve counting problems in which some elements are indistinguishable. Moreover, in this section, we will explain how to solve another important class of counting problems, problems involving counting the way the distinguishable elements can be placed in boxes. An example of this type of problem is the number of different ways poker hands can be dealt to 4 players. Taken together, the methods described earlier in this chapter and the methods introduced in this section form a useful toolbox for solving a wide range of counting problems. When the additional methods described in chapter 8 are added, so that's going to come later, when we add that to the arsenal, we will be able to solve a large percentage of the counting problems that arise in a wide range of areas of study. So here are some theorems. And so the number of R permutations of a set of n objects with repetition allowed is n to the R. And so we can think of an example. I won't walk through the proof. How many strings of letter R can be formed from the uppercase letters of the English alphabet? And so that would be 26 to the R, which is the number of R permutations of a set with an alphabet of 26 elements. So now we can be thinking of another example. Think in terms of money. So how many ways are there to select $5 bills from a box containing at least 5 of each of the following denominations: 1, 2, 5, 10, 20, 50, and 100. So we can place the selected bills in the appropriate position of a cast box as listed below. And some possible ways of placing the $5 bills can be shown here. And hopefully the graphic is clear enough for you to be seeing that. The number of ways to select the 5 bills correspond to the number of ways to arrange 6 bars and 5 stars in a row. This is a number of unordered selection of 5 elements from a set of 11. Hence, there are C11, 5, and then figure that out. It's 462 ways to choose 5 bills from 7 types of bills. So here is another theorem. The number of combinations from a set with n elements when repetition of elements is allowed. And so here is the theorem. I'm not going to walk through the proof. Once again, trying to keep this highlighted. at a high level and just focus on the concepts. So as an example, how many solutions does the equation x1, x2 plus x3 equals 11 have, where x1 and x2 and x3 are non-negative integers? And so we have the solution, and it turns out that there is a total of 70 possible solutions. Here's another example. Suppose that a cookie shop has 4 different types of cookies. How many different ways can 6 cookies be chosen? And so here we have that C96, which is also equal to C93, and that gives us a total of 84. You might remember this when we had that kind of come up, where there's a couple situations where they end up being that way. So here is a useful table that summarizes the formulas for counting permutations and combinations with and without repetitions. Are permutations, are commutations, are permutations, are commutations. So we allow repetitions, we have these equations. And then if we don't allow combinations, and then if we do, here is the modifications that we would use. So thus, this is what we want to take to the bank. This is what we want to be remembering as we go forward for these type of situations where there's repetitions. So we have some examples. I mentioned this, how many different strings can be made by reordering the letters of the word success. So this gives you how we would come up with a solution. And we come up with a value of 420. So it can be generalized into the following theorem. So keep that in mind. The number of different permutation of n objects where there are n1 indistinguishable objects of type 1 and 2 indistinguishable objects of type 2, all the way up to n to the k indistinguishable objects of type k, is n factorial over n1 factorial, n2 factorial, all the way up to nk factorial. So that's the general way that we can be looking at that. Well, what about thinking about distributing objects into boxes? Many counting problems can be solved by counting the ways objects can be placed in boxes. And so this could have quite an array of applications. The objects can be either different from each other, so that would be distinguishable, or identical, which would be indistinguishable. The boxes may be labeled indistinguishable or labeled indistinguishable. So indistinguishable objects with indistinguishable boxes. And so here we have the equation for the ways that we can distribute them. We can also see some exercises in Rosen that can play that out. And an example, there we have this equation, ways to distribute the hand of 5 cards to 4 players. And so we're using that equation to be figuring that out. And this is, I believe, is something that we've already covered. And so that's for distinguishable objects. And then indistinguishable objects, we use this relationship that we got introduced to. And so if we wanted to look at how we could place 10 indistinguishable objects into distinguishable boxes, we come up with this, and there's over 19,000 ways in which that can be done. Here's just some more examples. And so distinguishable objects and indistinguishable boxes, there are 14 ways to put 4 employees into 3 indistinguishable offices. So you can read through the rest of this and think about it. And then in terms of indistinguishable objects placed in indistinguishable boxes, there are 9 ways to pack 6 copies of the same book into 4 identical boxes. And so if you look in Rosen, this first one, it's covered in example 10, and the second one is covered in example 11. Okay, well, that's what we're going to cover for this lecture. Thank you very much for your time.